Welcome to our report on acid rock drainage and the effects on water quality. This report is being presented by Brian M. Lawless for the Environmental Science 546 Drinking Water and Human Health class, presented by Dr. Mahler at the University of Idaho. A quick overview of our presentation. Mining has a long history in Idaho, and the effects on the environment can be dramatic, and that's why I chose to do this for my presentation today. So it's going to start with a little bit of an introduction about what acid rock drainage is. We're going to talk about the chemistry of acid rock drainage, how that drainage makes its way into the water systems, the impacts of acid rock drainage on the environment, current methods for remediation and treatment, and future considerations when we're looking at acid rock drainage. So what is acid rock drainage? Well, in the simplest terms, it's the acidification of water that occurs when it interacts with rocks. This is actually a natural process, but is often referred to as acid mine drainage because it is common near mines. I'd like to give you a quick overview of one example in particular. This is the Gilt Edge Mine Superfund site, located just outside of Leeds, South Dakota. This site originally opened in the 1930s and worked for about 20 years when it was shut down due to gold prices. In the mid-1980s, it was reopened by a Canadian company known as Brome Mining Company, and at the time, they were only asked to put up an $8 million deposit because there was not any suspicion that acid mine drainage was an issue at the site. Shortly thereafter, in 1992, the site started leaching acid. BMC put in pumps and treatment systems, but by 1988 they were overwhelmed and were threatening bankruptcy. At that time, the governor of South Dakota actually started paperwork that would make this a Superfund site if something went wrong, because he understood that the state couldn't handle the issue. So by 2000, BMC did declare bankruptcy, and the site was immediately declared a Superfund site. At the time that the site was turned over, there was 150 million gallons of untreated water and millions of cubic feet of cyanide heap leach piles. Now, the reason that I have more every day written on here is because this is actually a groundwater seepage issue. As the groundwater seeps through the mine, it becomes acidified. So even though there was 150 million gallons at the time, there's more created every single day at this site. So far, about $60 million has been spent on cleanup. That's operations, facilities, infrastructure, and they estimate that they still need $100 million in order to complete the final restoration of the site. So how exactly does acid rock drainage happen? What is the chemistry that's going on? Well, in this formula here, we can see that we have iron sulfate, which is the FeS2 on the left side of the screen, also known as pyrite. And pyrite is a common mineral that's mined for the iron content, but what happens is that mixes with oxygen and water, then we end up precipitating rust, which is known as yellow boy in the mining industry, but it's something that everybody's very familiar with. We also get sulfate and a lot of free hydrogen atoms in water, which is actually what's known as our acid. Eventually, the sulfate and the acid can combine and form sulfuric acid also. So how does this acid get into the water? Well, as groundwater moves either along the surface or through the ground, it eventually will pop up to the surface and it'll interact with the surface water. Here is a case of that naturally occurring in Rockford, South Dakota at the Black Fox campground. There's a natural acid seep occurring right here that you can see in this photograph, and I actually was at this site a couple summers ago and measured a pH of 3.5, which is actually quite low. So why do we interact so much with sulfides? Well, many of the sulfide deposits are actually mined for the metals that you find in them. And here on this table we show some of the more common sulfides that are mined in Idaho. Some that are very popular are galena, which is a lead mine, molybdenite, which is mined for molybdenum, and of course gold should be on here. Sphalerite, cinnabar is another one that we have a lot of here in Idaho. That's a mine for mercury. So the drainage into the water systems is not a waste product of mining. There's a lot of misconceptions that acid is used in mining and then that leaches out into the soil, and that's the cause of all of the heavy metals. Although heavy metals are used in mining, In this case, I'm actually referring to something different, which we'll explain a little bit later. One of the things you can see here is when somebody goes into a hillside and they bore a hole, you can imagine the surface area around that hole gives a lot more surface area for interactions between water and oxygen and the sulfides that are in the soil to happen. So as we would normally see a natural process just happening on the surface, when we start drilling holes and crushing rock, we end up really increasing that surface area and dramatically increasing the rate at which oxidation takes place. This happens both in mine shafts and in pit mining. Again, this picture on the right is from the Gilt Edge mine in South Dakota, and you can see with the results of the giant pit that's been dug here, which is sort of misleading, this picture. It's actually about the size of 3 or 4 football fields, so it's a few acres in size, this pit. And the wall of material that's been exposed to water now ends up causing a lot of oxidation. Another great cause is mine tailings. When somebody digs the ore out of the ground and they crush it and they extract what they need, they end up dumping all of the leftover material into tailings piles. One problem that can happen, as you see from the image on the left, is that the tailing piles will sit on the surface, rain and snow falls on them, the water percolates down through the pile, eventually leaches into the ground and gets picked up by the groundwater and transported that way. Another option, sometimes they don't leave the tailings piles, they'll dig big pits, process the rock, and then put the waste right back into the pit, in which case you can see that groundwater can flow through that pit and end up transporting that acid now into the groundwater that way. So what happens when all of that water reaches the surface? Well, some of the most common issues that we'll see are rust discoloration. That's something that a lot of people see. This is that yellow boy precipitating out of the water. Once the water hits a natural water source, like some fresh water, the pH will actually start to rise back up, and all of that rust precipitates out because that material is a little more common in the acidic water than it is in the basic water. Also, we'll have increased water temperatures. The oxidation reaction is actually exothermic, and when that increases the water, the warm water drains into natural water bodies, and we have increased pathogenic activity because they prefer the warmer waters. Warmer water also holds less oxygen, which is bad for fish. And then, of course, the acidity level drops and the acidity level rises and the pH drops. And that becomes a harsher environment for the fish and the plants that were there before the ARD got into the water, and in some cases it's actually completely decimated all the flora and fauna that lived in water. And finally, the last issue is increased heavy metals. That acidic water is more likely to leach heavy metals out of the ground as it moves through. So you may have had water that normally would pick up just a little bit of arsenic and cadmium, but now that the water is acidic, it's able to pull more of that out and transport it. And as we know, heavy metals can lead to neurological issues, not only in people but in animals. So what are the effects on our drinking water? Well, as you can imagine, the acidic nature, the water quality that we just talked about causes some issues for water treatment plants. With the increased pathogen, increased heavy metals, and discoloration, which is a secondary water quality requirement, you end up with a greater need to treat the water. So now all of a sudden public water systems have to up their game and process a lot more water in order to keep it clean, or add more filters that maybe they wouldn't need before. And then the second biggest issue is damage to the water treatment systems that occurs because of that low pH. This could end up dissolving pipes and you get ruptures. In rust, you actually get that rust flaking and it ends up ruining and clogging galvanized pipes. So as far as our drinking water is concerned, it makes a big difference because the water itself becomes undrinkable, and so in countries where they're still drinking surface water or not treating their water, it can be a big health issue. And in developing countries, which we'll talk about a little bit later, that's going to be a real problem because the water gets contaminated and the water is not treated there. You can see here some photos of copper pipes and galvanized pipes that have suffered from corrosion. So how do we take care of it? Well, the number one way would be prevention. So let's see if we could keep that acid mine drainage from getting into the groundwater in the first place. We can do that by sealing underground mines so they can actually go into all those mines that were dug out into the hill, and they can flood them with water and then cap the ends so that water no longer flows through those tunnels. However, that's only effective if the rock in which the tunnels are built is actually impervious. It doesn't do any good to cap the ends and flood it if you just turn out that all the water just seeps right back out. There's underwater storage. This seems kind of counterintuitive, but what it's really doing is it's preventing the oxygen from getting into it. If you use water that has a very low oxygen content, then you really slow down the rate of oxidation. There's also sealed waste heaps, which is what we have a picture of here. We would have the pile of material sitting on top of an impermeable base, whether that's clay or some sort of material that we lay down. Then we seal it all up, cover it with topsoil, and we end up with this nice mound, and underneath of it is a bunch of rock. And as long as we can keep water from entering and flowing out of tailings, then we can prevent this acid mine issue. Again, this isn't a chemical that was added. This is strictly from the increased surface area that we get as a result of mining. There's also microencapsulation, which is coating the rocks and then just putting them out so that they don't interact with the surface. Although personally, I have a little bit of an issue with that because it seems like eventually that microencapsulation itself would wear out. There's anionic treatments, and then blending waste materials. Blending waste materials would be taking a basic waste that you have from one place and mixing it together with the mine tailings that you have, and the end result would be a neutral runoff, because it's not the chemicals, it's the acid that we're trying to take care of here. If you can't prevent it, now you have a problem. Now you have to actually treat the acid mine drainage. So you can imagine going to an old mine that's been leaking for a while. Yes, you can pick up the tailings, you can seal them, but you still have all of the acid that's in the ground already, so you have to take care of that. The most common method by far used today is lime treatment. Lime is another word for calcium carbonate. It's a very basic material, and so when they mix it with the acidic material, you end up neutralizing things. In lime treatment, the goal of the treatment plant is to raise the pH up to 9, at which point most of those heavy metals that have been migrating with the groundwater will precipitate out into what's called a high density sludge, and then it can be removed from the water, and the remaining water is typically neutral enough and low enough in heavy metal concentrations that it can then be discharged directly into either ground or surface water. Problem is, this is expensive. It has to be maintained. The Gilt Edge mine, as of 2000, the annual operating costs were about $2 million a year just to keep these pumps going. You can see here the size of the facility that's required. All of those tanks that you see on the right hand side of the picture are actually calcium carbonate tanks, where they store the material that then gets pumped into that big house and mixed into the groundwater, sent out to a settling pond, and then eventually pumped from there into a nearby stream. It also requires an adequate supply of lime. In South Dakota, this is easy because there's a lot of limestone in the area, but if you're not in an area where lime is common, then it would be difficult to maintain the volume that you need in order to use this process. But this is by far the most common one used today. So some of the more emerging treatment methods, they're trying to focus on a more natural based and passive method that isn't quite as expensive. The most popular one right now is aerobic wetlands. So wetlands tend to have a pretty basic pH already. So if you can send your mine discharge out into either a natural or a constructed wetland, like the one that we see in this photo, then you end up giving time for dilution, you get settlement of metals, you get all the filtration that happens from the plants and animals that live in that wetland, and it really is a pretty good system, although it requires a lot of space in order to do this. Second most common one right now is anoxic limestone drains. You can see in this photograph someone's just putting in a sealed drain, and you just pump the wastewater into the drain. As it moves through, it reacts with the limestone, lowers the pH, heavy metals fall out, raises the pH, heavy metals fall out, and then the water gets discharged at the other end. Bioremediation is a new one that's really coming up that's using bacterial processes to actually consume or take up those metals that are in there and balance the pH, and then those can then be extracted and incinerated or whatever it is they do with them. Reactive barriers is kind of a neat idea. It's similar to the anoxic limestone drains. The water passes through some sort of a barrier, and as it passes through, the acids are neutralized, and then it can enter into the groundwater. So what do we need to know about looking into the future when we're considering acid rock drainage or acid mine drainage? Well, the biggest thing is that the problem can still occur. We could go out today and take care of every known issue, and then just like at the Gilt Edge mine, they can pop up later. All this reaction is taking place underground, and until the ground migrates, or until that water migrates to the surface somewhere, we're not aware of the issue. The other biggest problem that we're going to see is in developing countries. Most commonly in Africa is the big hot spot right now, where the need to fund a growing economy outweighs environmental and personal safety. Also, these countries often don't treat their water. So if we have an area where we're causing a lot more mine waste and then not treating our water, there could definitely be some public health issues that have to be dealt with there. We are going to see improved remediation methods that are going to become more affordable and easier to deploy, that won't require maybe such a big facility. And then, as we already see, regulations and mining practices are changing, and those are mostly focused on prevention. If we're going to go and we're going to set up a mine, let's do it right so that we don't have this problem in the future. With that, that's all that I have for this presentation. If you'd like any more information, you can refer to any of the references that are listed here, or refer to the report that accompanies this presentation. Thank you very much for your time.